Inverse functions are functions that undo each other. This is common throughout mathematics. We have different functions that, again, carry out this idea of undoing one another. For instance, if we had x cubed, its inverse would be the cube root function. Those two operations cancel each other out. We could also consider x squared and the square root of x. Those are two operations that cancel one another out. In this case, with the domain restriction that x has to be greater than or equal to 0. So we can identify any two functions as inverse functions by testing a few things. First, we can start off by testing an individual point. We can look at evaluating h of 0, where h is the function that we started off with in example 8. This would give us 0 plus 3 over 0 plus 4, or 3/4. If we plug that value of 3/4 into the inverse function that we found, so h inverse, then we would get 3 minus 4 times 3/4 all over 3/4 minus 5. This would reduce down to 3 minus 3 over 3/4 minus 5, which we're not concerned what that is, because in the numerator we get 0, and 0 over anything would give us 0. What we can see here is that we start off with this value of 0, plug it into our function h, take that result, plug it into the inverse function, and what we end up with is that same value. Essentially meaning we have two functions or two operations, which are a little bit more complicated than just cubes and cube roots, but two operations or two functions that undo each other, get us back to that starting value. If two functions f and g are inverses, then both of the following statements have to be true. We have to be able to say that f of g of x is equal to x, and that g of f of x is also equal to x. So we need to take both compositions in both orders and verify that the end result for both is equal to x. If we can do that, then we know that for all values of x, these two functions are inverse operations because they undo each other. In order to test this for our results from example 8, we can look at first evaluating h of h inverse, meaning we'll evaluate our function h for 3 minus 4x over x minus 5. This will give us 5 times that quantity, plus 3 all over that quantity plus 4. From here, we can multiply both numerator and denominator by x minus 5, which will simplify our rational expressions. This will leave us with 5 just times the quantity 3 minus 4x plus 3 times the quantity x minus 5. In the denominator, we'll have 3 minus 4x plus 4 times the quantity x minus 5. What we'll do next is distribute through to get 15 minus 20x plus 3x minus 15 all over 3 minus 4x plus 4x minus 20. In the numerator, 15 minus 15 will cancel. In the denominator, minus 4x plus 4x will cancel, leaving us with negative 17x over negative 17, or just x. So we've confirmed that h of h inverse is equal to x. That takes care of part 1. We also need to confirm that h inverse of h is also equal to x. This means we'll be taking our inverse function and evaluating it for 5x plus 3 over x plus 4. So we'll get 3 minus 4 times that quantity, all over that quantity, minus 5. And then what we can do is multiply both numerator and denominator by x plus 4. Which will give us 3 times that quantity x plus 4 minus 4 times just the quantity 5x plus 3 over 5x plus 3 minus 5 times the quantity x plus 4. Again, we'll distribute through to get 3x plus 12 minus 20x minus 12 over 5x plus 3 minus 5x minus 20. In the denominator, our 5x's will cancel. In the numerator, our 12's will cancel, which will leave us with negative 17x over negative 17, which again is equal to x. So we verify that both of those compositions leave us with just x, which verifies that this expression that we came up with for the inverse of h is in fact the inverse of that original function h of x.